Okay, making another code here. We're trying to code universal gravitation. So big G problem. So G mm over r squared for the force magnitude and negative G mm over r for potential energy, that kind of stuff. Let's start with the screen share. Maybe. Did I forget to click the button? There we go. All right, so let's see here. This is going to be your starter code, I think. So let's walk through it here. Just some standard coordinate system. Notice I put in the constant. Immediately, we could tell right away we're going to need some scale factors here. All right. With this number, we could see the numbers are going to be out of control in this problem if we don't think very carefully. So at any point today, if you see arrows that are way too big or too small, you may need to adjust the scale factor dramatically by powers of 10,000, maybe even a million. So kind of be a little patient with yourself as you have to play around with the scale factor occasionally. That said, I believe these numbers will get you in the ballpark first, so at least for the first code, you could see things. So I'm imagining two rocks deep in space. So I'm going to call them rock 1 and rock 2. I give them some positions. All right. And I give them some masses. I define some attributes and I give that to them. Great. So it looks like one of them is going to be orange and one of them is going to be cyan, whatever. Now, in general, we're going to have a vector that goes from 1 to 2. And so from 1 to 2 means 2 is the final and 1 is the initial. So this is the classic equation, basically R final minus R initial. That's what this equation is. From 1 to 2 means from 1 to 2, final minus initial. Be careful with that. Minus signs screw up everything if you aren't careful. So you're going to need to compute the force. So you may need to look up how to do a hat vector again, or in practice, it turns out you could, rather than do r hat over r squared like this, r hat over r squared, you could also do r vector over r cubed. So I'm going to let you figure out how to write that line of code and make sure it's working. Then you're going to need to draw an arrow. Now, these lines of code don't make sense right now because you haven't calculated the force yet. We could even just make this, yeah, well, let's not. But the idea here is these lines of code, if I comment them out for a minute so you can see them better. Saturation level. Okay, why are we going to need that? And what is it? Well, in this problem, notice there's going to be an r vector over r cubed or an r hat over r. Basically, we're dividing by r. Now think, it's quite possible as you're playing around in the code, you may start to get the two masses very close together. As they get closer together, you have a 1 over r squared. The forces are going to explode and get huge. So not only do we want to include a scale arrow, right, which kind of limits the size of things in one way, we're also going to put in a saturation level, which is a hard limit beyond which we don't let the arrow grow, at least in terms of drawing it. The force could be huge, but we can't draw that huge force at some point. So it's basically setting an upper limit on a value for the size of an arrow. This is very different than scaling all the arrows by the same amount. That's what we've been doing till now. So in this case, we're going to check if this scaled arrow, so again, we're going to use the scale factor and scale it. But if that size of the scaled arrow exceeds the saturation level, we're going to lock that arrow down to a size 10 arrow in the direction of the original force vector. And this is what I was saying. Now this doesn't know how to compute because this is commented out. So you're going to have to do some work here. And then otherwise, it's going to say, hey, just draw the arrow as the scale factor times the force vector. So this basically allows us to use both a scale factor and an upper limit or a saturation level. So that's what that is. Let me comment this out so I don't forget. And then you could also compute the potential energy. I think you could figure that out. And then I've got some print statements prefabbed for you here. And to save you some time and some hassle, I finally bothered to put in the formatting for sig figs. So this is called an F statement. And what this does is this says, hey, format whatever's inside these curly brackets. So let me uncomment these for a minute just so you can see better. Okay, so this is going to print out the gravitational force. Notice that's a vector, right? It should be a vector if you do your work correctly. Otherwise, this code's going to have trouble. Next, print, and I've got an F statement. It says, okay, go inside the print statement. I'm going through it. Keep reading, keep reading, keep reading. The code's reading, reading, reading. Aha, I see this curly bracket here. So this thing inside the curly brackets, we've got the magnitude of the force, right? And this tells us how many decimal places we want to format this to. They may say, why didn't you do that on the vector? Well, remember the vector is 3 separate numbers. Excuse me. And so I didn't want to take the time to go through format each one separately. If you try to stick this on here, I believe you get not a number as an error. But you could try and figure out how to format the vector if you want to waste the time on it right now. But so this is not going to compute because we haven't done any of the real calculations. I'm leaving that for you to do, right? You're supposed to figure out how to do the forces and the potential energy and print them out. But I will go ahead and show you here. I think I've got the solution typed up somewhere. And let's just run this code and hopefully it works. There we go. And so if I could, I'm just going to shorten this up. Whoops. So you can see this on there at the same time. And let me zoom in quite a bit. Whoops. I'm trying to zoom in just so you can see this. There's the X, Y, and Z axes. All right, there we go. And so now notice here's the gravitational force. And notice this actually did the sig figs for you there. And so you've got an idea of what the answers are now. So hopefully you can code this and you know what it should look like. All right. And once you get that done, you should be able to make your own while loop and animate the motion, right? So you could do set time equal to 0 and you could animate it. And then be careful. We've got to use the Euler-Kromer method. So when you're animating the motion, if I could here, maybe, oh, whoops. Sorry, Zoom's lagging on me. Sorry, just waiting for it. Okay, oh my gosh, there we go. All right, so when you're doing the Euler-Kromer method, geez, this is really laggy right now. You know what? Let's stop the screen share and just go to the whiteboard. So when you're doing the Euler-Kromer method, let's think what you want to do. So the order matters. We want to do force. And then, so let's say update force. Right? The first thing you need to do is each time the object moves, you need to get the correct value of force. Then use that correct value of force to update momentum. Let's just say P. All right. And finally, you could use that to update the position. Okay. And don't forget, you probably better do a T plus equals at the end. Whoops. And so that will walk you through the process of animating the motion of this thing. Now, I think there was something I was going to mention. Oh, so there's actually 2 masses here, right? So you're going to have to do this twice. Now, you could argue, is it worth it writing a function or not? I don't know. I didn't bother writing a function. I just updated everything and was very careful updating the first one and then just copied and pasted that whole section of code and updated the subscripts to get the other one to run. And don't forget, you could always use, we know Newton's third law, right? So once you figure out the force that 2 exerts on 1 or 1 exerts on 2, hopefully you could use Newton's third law to very quickly figure out the other force to save yourself a lot of annoying calculations. All right. And then you could add a third mass. And then you could have all animate. and see what happens. And you could do some other exciting stuff too, like try and figure out what the predicted escape velocity is, right? You could say, okay, well, I'll do a little calculation and I'll give the ball some initial velocity and see if it can escape from the other ball, things like that. All right.